10, oh, that's that they escape and don't do anything.
Not that they escape from the core, no.
It was absorbed in resonance.
The resonance escape probability that they didn't get, the probability they didn't get captured or absorbed on their way down through energy space. Remember those big jagged cross sections in the middle of the energy region? That's them. So let's think why that arises, because where we blithely put up a moment ago, oh, it's the rate of production divided by the rate of absorption. Well, the production of neutrons, we actually produce fission neutrons, but we were talking about the absorption of thermal neutrons and the absorbing of thermal neutrons in a fission reaction, i.e. the sigma F part. But again, it was thermal neutrons that were being absorbed there, but we're actually making the fission neutrons. And it was just one of the various ways that this simple diffusion theory can be tweaked a little bit to take into account some of the grosser approximations that are involved. So there was one, indeed, putting in those couple of factors to try and allow for the fact that really what we are quite brazenly, bravely, rashly modelling as a single soup of thermal neutrons only actually has got energies ranging by a factor of 10 to the 8, between fission neutrons that are born at 2 MeVs and thermal neutrons that do their business for us at 2% of an MeV, 2/100ths of an MeV. So whatever that is, 10 to the 8 times. Okay, so we're done with criticality, and for the second half, which is probably shorter, I think, maybe it's just as well. Let's have a look at time dependent part. Remember, that was more or less where we started the morning. I think that's the conservation statement plus the diffusion approximation. There's the d times the diffusion gradient, instead of div of j, it's d times d grad. Either we can talk in terms of point kinetics, which is a bit like saying we'll look for a separable solution where it's separable in space and time, so we can just take out the time dependence and accept it's going to multiply the spatial dependence. That's one perfectly valid and equivalent way to do it. Arguably even simpler. Okay, well, let's just see how an infinite reactor behaves. Tells us much the same thing. But in either case, we get rid of all the spatial dependence. So we're left with dm by dt equals those two terms over there. And we're used to our source term as being the source of neutrons from the fissions. That's what we're just talking about. But this is where we have to accept, actually, it's not quite that simple, but it's nothing like that simple. Whilst we use mu as the number saying we get on average in total 2.5 neutrons per fission, whatever it might be, some of those neutrons that we counted in there in defining that number mu were actually neutrons that came sometime afterwards from the decay, radioactive decay, of fission fragments. Because a few of the fission fragments give off neutrons just like they give off alpha particles, beta particles and gamma rays. A few of them also give off neutrons. And we know that fission fragments tend to have more or less the neutron to proton ratio that their parent had. It was a big nucleus split into two. So they will have a neutron to proton ratio more or less appropriate to a very much bigger nucleus. Not quite, because they've lost 2 or 3 immediately, but they've still got a lot more than really they are, I won't say entitled to, I guess, who knows, but more than they're comfortable with. And one of the ways that they will reduce the number of neutrons per proton is simply to keep one out. Fine, that's the obvious thing to do. What's What's another way in which a fission fragment typically, and frankly much more commonly indeed, reduces its neutron-to-proton ratio? Beta decay. That's the double whammy one because it reduces the number of neutrons by 1 and increases the number of protons by 1, so it's 2 for 1, I think. Anyway, the other way that a few of them do it, thank heavens, because without that, the light needs to be able to job, I suppose. Maybe. Oh, wouldn't quit another job to join this one. I was in oil, I was covered, you see, I could go either way. One of the ways they'll do it is by the decay, and a fraction, small fraction, beta of them here, were the neutrons that were going to appear by the decay of the delayed neutron precursors. So we reduce the source rate that we've had in the past to allow explicitly for the fact actually that's the prompt source term now, the essentially immediate source term, and the rest of them will show as coming from the decay of the delayed neutron precursors. And if there are quite a few of these, half a dozen or so, and if each of them has got a concentration of C, Ci I've called it there, and each has got a decay constant lambda, the rate at which they're generating neutrons, each of them is lambda times C. So, oh hello Keith. Thank you. There you go. Okay, good. You do it for that, was it? Keith, I'll drop your lecture to you with hydraulics. No droppers here on the start. That's the decay of each of those delayed neutron precursors, making up for essentially the ones we're no longer getting, or never did get anyway, but we're no longer treating them as if they all came via the same process. So we put that source term into here, and that gives us that for our dN by dt. A couple of things, we've got, if we divide through, we'll find we've got a 1 over V times sigma A popping up, and that has dimensions of time, so we'll call that L, and we'll see in a moment that that's a lifetime, but for now it's just 1 upon V sigma A, and we're choosing to call it L for convenience. We're introducing reactivity K infinity minus 1, and putting those things in, we end up with that equation there, just some simple algebraic tidyings up to get us to that. Well, that tells us, gives us an equation for dN by dt, but obviously it involves C, so we need to know what the C's are. And of course, the C's involve N, because if we write an equation for what is the time-dependent concentration of precursor C, we can write down a balance equation for it. What's its rate of change? Well, it's being made by fissions and it's being destroyed by decays, so that's its balance equation. It's being lost by decays and it's being made by fissions, so with the fission rate times some fraction beta is the rate at which we are reducing the precursor C. So there's a differential equation like that for each of the 6 or 7 precursors, and there's the differential equation above, just the one of them, for the neutron flux or the neutron number density itself. So of course they're all coupled, they each involve each other. The C's feature, the C and the N features in this, and the C and the N features in this, so it's all one big mess essentially. Well, solving those is troublesome analytically, to put it mildly. Happily these days it's fairly trivial numerically. Packages like MATLAB have very easy to use package solvers for couple those these at that time. We can actually solve them and get a lot of information. If we do that and plot it out, you get the graphs that are there in the output of the MATLAB scripts that I have made available to you. And I would encourage you to use them and look at them and play with them. You'll see the forms of the behaviour, and at least to have a physical, to see what the form of the equation of the behaviour is, and to be able to describe physically what's going on is obviously important. We don't, here in this course, require that we do any more algebraic manipulation, but things like, as I put there, understanding the form of the solutions, understanding physically what's going on with the prompt jump and the prompt drop and the subsequent fairly steady e-folding times that result. Getting an appreciation of that, in part, I would suggest, by playing with the MATLAB solutions of them, is very important. And the other thing I put down there, why there's a bracket at the end of it, just suggesting to make sure you understand that physical interpretation of the quantity L. And remember that we said, well, we could actually picture the target material, or the material through which the electron is flying, and think of in the cross-sections of each nucleus as like dinner plates, glass boards, and obviously depending on how big that is, would affect how far into the material you have to go, how big and how dense together the nuclei are, of course, would affect how far into the material you needed to go before on average you're likely to have hit something, by how thick a block of it till you can't see much daylight through it. That's really all we're talking about. And we can see that that then gives us a measure, that quantity that we had, the V and the sigma A, we can interpret that as related to the time of flight that the speed comes in, the time of flight that the neutron would be moving for until it hit something and got absorbed. So that's an interpretation of that quantity, V times sigma A. The other very important takeaway from that, of course, is to be able to look at that and think, okay, so what's the behaviour going to become like when I allow my reactivity to approach and go beyond the value of beta? So that's when you move from, when the reactivity is small compared to beta, small positive, let's say, the reactor will behave more or less as if it had got neutrons with a lifetime, the weighted average of the prompt rather, and the delayed neutrons. It's a tiny number of delayed ones with very long lifetimes. Most 99 point something % are prompt ones with a lifetime of 10th of a millisecond. The weighted average of those is whatever. And for small reactivities, it will behave small relative to that quantity beta. It will behave more or less like a reactor with single lot of neutrons with that averaged lifetime. But as the reactivity approaches beta, as you might expect, we move into very different territory, and at beta and beyond, it behaves more or less like a reactor where the lifetime is the lifetime of only the prompt ones. So we move from a slow doubling times to very, very abrupt doubling times. So plainly that's a bad thing if you're designing a power reactor. It's a good thing if you're designing a bomb. So if that's what you want from the point of view of a fission bomb, you want to make sure it is prompt critical so the power can rise very rapidly so it will blow itself apart, which is the objective. So that was our kinetics. Then the last thing I wrote a summary of, but we're now getting very, very close, we did it last week anyway, was just a brief bit about xenon that we got from your notes. First one, that little bit there, we just went through the very straightforward demonstration that the change in reactivity by adding a bit more absorption because of fission products was just the fraction that of that fission product absorption was of the previous absorption in the core. So change in reactivity, just the fission product, the extra absorber, whatever it is, cross section divided by the original. That was really just to give us something to refer back to. Because the whole point of this next part then was to try and understand the life cycle of a couple of the most important isotopes produced during the fission process. Certainly most important as regards their reactivity effects. As we start off with a core where we've carefully computed our criticality and said we need this composition for this geometry and so on and so on, we've done all those fine sums, and then we go along and completely butcher the composition. Because the minute we start causing fissions, we generate pretty much every isotope under the sun. More than that, we generate ones that don't exist here of their own anyway. And those have big cross sections for absorption amongst other things. So having carefully got our composition sorted out, we then go and pollute it. So we need to know what pollution are we going to cause, how are we going to change our composition, and make sure that we put in at day one enough fuel to allow for the fact that days or weeks or months in will have built up lots of poisons. We also, of course, then need to make sure that we put in enough extra absorber at the beginning to make up for the extra fuel at the beginning, so that some way down the road when we've made ourselves some more absorber, okay, we can still be critical, but we aren't overly critical right at the beginning. So that long-term reactivity control, the provision of lots of temporary absorber to cope with the excess fuel at the beginning, and that temporary absorber has to be taken away one way or another. You can see it starts to look quite a complex problem to design the reactor so it can cope with its real life power history and burnup and so on and so on. Certainly it's very, very large amounts of reactivity associated with these changes have to be provided at the beginning. Anyway, so the one we looked at in particular is xenon, but understanding xenon involves also understanding, as it happens, iodine. Iodine 135 and xenon 135 both are working in tandem here to give us an entertaining topic. So we're getting some fissions happening, some rate 5 times sigma f. Some small fraction of those fissions will simply result in xenon as the fission product, and the terminology or the notation that's normally used there is fission product yield. So you talk about the fission product yield of iodine 135 or xenon 135, so it'll be a number, a pure number, dimensionless number, well less than 1, because we're making dozens of different isotopes. So it'll be 0.0, well it's in your tables no doubt, I've given you the numerical value. So 1 or a few percent of fissions will result in 135 xenon, and 1 or a few percent of fissions will result in 135 iodine. So we've got the respective production rates of those two isotopes. So this box here, which I'm drawn to try and represent my stock of 135 xenon, I'm adding to it from this process, but I'm adding to it also because the 135 iodine, once we have made it, decays and generates 135 xenon, and it decays with its own decay constant, lambda. So I've got a rate of pumping in of xenon there of lambda iodine times n of iodine. So that's 2 inlet processes into my xenon population, and I've got 2 ways in which it's being removed. One way here, and there's no significance to the length of the arrows if one's big or one's small. The xenon itself captures neutrons. That's why we're interested in it, so plainly it's going to capture neutrons. And of course when it captures a neutron it ceases to be 135 xenon, it becomes something else, so it's gone. It's a different species, one we care less about. So we'll lose xenon at the rate of its cross-section times its number density, phi times n, sigma, I beg your pardon, sigma times n. And we'll lose it also because it simply decays, it's got its own decay process with a decay constant lambda, so we lose it at a rate of lambda times n. So two ways we're making xenon, two ways we're destroying it. One of the ways we're making it itself depending on the decay of something else that is being made by another process. So there's a fair bit going on. And to understand all of this ins and outs, then we have to write down the equations for each of them, and well, I did say try and solve them. Actually, I've written a note in a way you don't need to solve the equations. We can pretty much get what we want just by looking at the equations and pull out the interesting information. Right. So just writing down algebraically. Two equations. We're just putting in there for the 135 iodine. We've got the fission yield times the fission rate minus its number density times its own decay constant. So that's the rate of change of iodine. The rate of change of xenon has got 4 terms rather than 2. Its fission yield times the fission rate. The decay of the iodine, which is a negative there, comes up here as a positive because it's decaying into 135 xenon. Its own decay, lambda of the xenon times n of the xenon as a negative, and minus the rate at which it's capturing neutrons and turning itself into something else. So we've got 4 terms there for the xenon. Well, those 2 equations in principle we could solve. Solve the first one, get the solution of that, solve the second, because it has to feed into the solution. And you can, you've got the notes that do that as you wish. But I don't include it formally in the course because it's more an exercise in solving ODEs rather than understanding some physics. The things we are interested is to know how the equations behave. Or we can make an estimate of what the, well no more than an estimate, we can work out what the long-term equilibrium level will be for each of those quite readily. Let's go back to the picture, because we'll do it from the picture most easily. The rate at which this is formed is independent of how much of it there is. It just depends on the flux and the fission cross-section. So we're forming it if we're operating at a constant power at a constant rate. It's decaying at a rate that is proportional to how much of it there is. So plainly it will rise in quantity until the rate of decay equals the rate of reduction. So we expect it to do that and level out. And we will find the plateau level, its equilibrium level, by equating the loss rate and the production rate, and just rearrange those to get out what is the number density at which that is equal, or at which those are equal. That's what we do to get the long-term equilibrium level of the iodine, and more or less the same for the xenon, but obviously it's a little bit more complex because there's more things going on. But if we do that, we'll do that for the iodine, we get that one, it's easy. Rearrange those. Equate the 2 terms and get the n on its own. But the other thing we estimated was the time to reach it. Well, we expected, as seen by you, to go up like that. What we did was say, well, let's make, we can evaluate what the gradient is at time naught. We know that would have shot up straight, but it's going to curve over, and it's going to decay exponentially. So we could work out how long it would have taken had it risen, continued to rise at its original gradient, which is going to be asymptotic to the value anyway, so there's no such thing as when it gets there. But it's going to be a few times that till it gets pretty damn close. So we could work out the time taken at the initial rate and say, well, 2 or 3 times that. But we're really only interested, are we talking seconds or a day or is it a year? That's what kind of timescale are we talking about? So we do that gives us our equilibrium time, which turns out to be 1 over lambda. Now we do the same for the xenon. So again, it's a little bit more complicated, but we do that. And that gives us pretty much all we needed from that, because once we know the long-term xenon concentration, we can work out what the negative reactivity is that flows from it. We know what that the delta rho, remember, was just the fission product absorption cross-section divided by the total original absorption cross-section. That's the reduction in reactivity. Okay, well, when we get to solve those equations and do it in a little bit more detail, we also saw the interesting effects when we shut down. I haven't done those in the notes here, but I found I was just reproducing what's not really extensively reduced very much from what's already in your notes. But if you remember when we shut down, I think what happens to the So what happens to the xenon concentration on shutdown? Well, that stops for us to begin with. Phi goes to 0. That goes to 0. So both of those processes cease. This process continues. This process stops. And that one continues. So you'll see we've got a xenon production happening from the decay of iodine we made earlier, and we've got a xenon decay of the xenon we already made earlier. So it's the balance between those two things and their respective time constants. If we go through and look at the algebra, I haven't done it on the board now because it's in your notes from last time, we'll see that depending on the level from which we started, the behaviour might be such that the equilibrium level we got to, it more or less just drops off. But sometimes, depending on where you've been operating, it actually could rise before it finally falls. That was that very odd behaviour, which gives you the possibility that you could shut your reactor down, having been operating perfectly well, put an absorber, shut it all down, try and restart it a short while later, and meanwhile that xenon concentration has risen sharply, and you've suddenly got so much negative reactivity there because you've shut down that you can't restart, which is practically, that's a circumstance it's very easy to get into. The xenon, that's one practical consequence of that. And the other one, if I were to use the phrase and say this would be of interest to reactor designers and safety folk, they'll talk about xenon honed down. There's a phrase that's often used. What do you think that might refer to? You're designing your control rods and shutdown system. Well, it's one thing to say, well, maybe we may not be able to shut it down. If you just shut down and then the xenon decays, you've got a very strong absorber that was there in the core that is decaying away busily. If you only put in a modest amount of absorber to shut the reactor down and make it subcritical, and then while you've gone away for the night or for your lunch break, that xenon decays away, that strong absorber is disappearing, so the reactivity of your core is busily rising. And it could easily be the case that the decay of the xenon adds more reactivity than you took it negative by, and you could actually go critical again. Well, plainly you make damn sure it doesn't happen, and it's one of the things you design the reactor carefully for, that you have enough what's called xenon hold down, that you always make sure you're shut down with enough negative reactivity to counterbalance the positive reactivity that the reactor, totally on its own, will add to itself over the next few hours. All sorts of embarrassments would follow. You know, the wretched thing started up in the middle of the night when you weren't there and blew up or boiled or whatever it did. It would be a relatively slow process, so it wouldn't blow up. You'd go critical. You'd approach critical reasonably slowly and probably bubble along there because the power would then rise and start to burn up some xenon and so on. It would be an interesting exercise to do, but it's not something we want to be happening, to have this unmanned reactor experiment happening in the middle of the night while you're tucked up in bed, upwind or hose. Okay, the last thing, again I haven't summarised it, but the last thing we did in the course, well, I'm not sure what the order was, but was reactivity feedback. Obviously this is a form of reactivity feedback. By feedback we just mean the reactivity of the reactor changing as a result of what the reactor itself does to itself. This is one. But more generally, there are probably the biggest class of feedback is to do with temperature. Yeah?
So, just a very quick question about poisons. Is xenon really the main consideration? Because you'll have other things like samarium, gadolinium.
Yeah, it's a trade-off, if you like. Their importance is a combination of the life, how much of it you make, obviously, and what its cross-section is. Yeah. So.
But xenon tends to be the
yes,
main
it's
design.
Yeah, and it's the one that changes in this most interesting way. It probably is the biggest, but it is absolutely the case that to design a core for real, you absolutely have to have some mechanism to understand the behaviour of many. In practice, you do pretty much for all. I mean, nowadays with computer codes, you simply do it for all. I mentioned one of your colleagues here is doing that for his fourth year project, trying to build a computational tool that takes into account large numbers of isotopes, but yeah, you do have to do that, and how they change and their relative importance will change over life. That's the other thing, and then you come and you swap half the fuel. So actually working out the reactivity of the core and the safety issues associated with it is most stations will have a resident reactor physicist who will be running simulations of this kind all along. Preparing for the next shutdown, so we'll be keeping track. You'll follow the burn-up of your plant, you'll make sure your models follow that burn-up, so you've got a pretty good idea of what your core is full of at any one time, and then you'll take those out. You say, I'm going to shuffle those from there to there, so you'll rerun all the reactor physics calculations with a changed spatial distribution of fuel, and then have to run that through the next 2.5 year prediction. Or if you're a submarine, you'll run it for the next 30 years. They're hoping their course will last 30 years, so it's, you can imagine that's quite a hairy process, trying to predict with sufficient reliability over that sort of period. And when you don't know, of course, what the power history will be, because it depends enormously on how you're operating it. Are you dawdling under the ice cap waiting to fire a bomb at someone, or are you racing around the ocean trying to catch another submarine? Who are you, kind of thing. So it's, there's a lot of uncertainties. Yeah, I answered your question. Yes, thank you. So we were talking about feedback, weren't we, more generally? So thermal feedback is probably the most an important one. What you'd like, obviously from a safety point of view, is if your reactor gets hotter, you'd like the natural intrinsic behaviour that it reduced its own power. And it's generally possible to engineer the reactor so it does do that. So temperature feedback, you'll generally try to arrange that it causes reduction in reactivity. To the extent, pretty much, if you try to get one licensed where that doesn't happen, you'll be turned down. Pretty much absolute. There are some very slow temperature feedbacks in the AGR, I think, which are positive, but they're so sluggish that you've got plenty of time to deal with them, they really aren't an issue. And all of the shorter term temperature feedback, whichever, are negative. But that raises the issue, what do we mean by slow and quick temperature feedback? And that's really important. And often it'll be described as being prompt and delayed feedback, which is unfortunate terminology because it's nothing to do with prompt and delayed neutrons, so just make sure you know what you're talking about when using those terms. The prompt feedback and the delayed feedback simply refers to how quickly the feedback comes after the power change that caused it. That's all we're saying. So, for example, a feedback that was related to the temperature of the UO2 in your fuel rod, would you think that was a prompt or a delayed one?
Prompt.
Yeah.
It gets hot very quickly.
Absolutely. Increase the power, first thing that happens is the fuel rod gets hotter. That's pretty reliable. Yeah. So prompt temperature feedback would be related, say, to the UO2 temperature. At the other extreme, or the most delayed feedback you could think of would be the reactivity effects of the graphite moderator temperature in a Magnox reactor. Great big sluggish, low power density, lots and lots of tons of graphite. Graphite is coupled only weakly in a thermal sense to the fuel. Okay, there are fuel channels and gas running up those, but there's big chunks of graphite in between. Graphite is kept cool by slipstreams of coolant gas passing through various passageways in it. And that's taken off there and comes in. So it takes a long time for the graphite moderator to respond to a change in, say, coolant temperature. It will do eventually to get a bit warmer, a bit cooler. So a very, very delayed thermal feedback. So long-term delayed thermal feedback rather than prompt. So they're probably the main sort of takeaway concepts from the feedback side. That probably has covered everything in that second half. Of course, there's not a lot in it, isn't really? We should tack more in for the next class next year. not a good work. Okay, so more quick, yeah? Just uncover that, yeah. You do have those equations anyway on paper, but yeah, those who have been actually writing them down, I think that is an excellent idea. You want to go further now? Tell me when to stop. Okay, slightly unconnected. I just, for other reasons, checked my diary. We have, I'm not sure if I circulated this or not, or how many know that we were trying to run a thermohydraulics tutorial next Friday at 8 AM? Yes, I don't know if you saw the rather unfortunate email trail. I was just trying to do the simple thing of sending an email to this class, and one department said, not our problem, mate, and the other department said, not our problem, mate, and then we're stuck. It's a half and half. So the ChemEng-based thermohydraulics course, which pretty much everyone here, I think, did take, by popular demand, as they say, I'll come along at 8 o'clock next Friday, so before this class at 9. Did I say a room in the email?
Yeah.
Where,
I think it's
the drawing offices.
yeah, one of the drawing officers there.